In this lesson, I'm going to show you how to construct Lewis structures, which is mostly a review of bonding and simple molecular shapes. Oh, okay. So in the localized electron model, that means that when electrons form bonds between atoms, they kind of stay put. And when you have a molecule, it's composed of atoms bound together by sharing pairs of electrons using the orbitals of the atoms that are involved. So when we talk about molecules, we're talking about covalently bonded substances. When we look at this localized electron model, we assume that the electron pairs are localized, meaning they stay where they are on a particular atom or in the space between two atoms. So the electrons involved in a bond between, let's say, carbon and hydrogen, for example, stay between the carbon and hydrogen and don't go anywhere else. There are two different types of electrons involved in these molecular structures. There are lone pairs. Lone pairs are pairs of electrons that aren't involved in bonds. They just kind of stay with the atom they're located on. And then there's bonding pairs, which are pairs of electrons found in the space between the atoms. Bonding pairs can be represented as a single line, or they can be represented as two dots. So just pick a method. Normally, students for bonding pairs will pick a line to represent a bond, and they won't use dots unless it's for lone pairs. There are three different things we can do with this localized electron model. We can describe the valence electron arrangement and draw a Lewis structure. We can predict the geometry of a molecule, the shape of it, using what's called the VSEPR model, which we'll talk about later. And we can also describe the orbitals used to share electrons or hold lone pairs. So what I want to show you here is how to draw Lewis structures and showing how the valence electrons are arranged among atoms in a molecule. And the whole idea here is that the stability of a compound has to do with its noble gas configuration when it bonds. There are a couple of different things here that smaller elements will follow what's called the duet rule, where two electrons are enough to complete its valence shell because it only has one shell. And then, of course, we have the octet rule, where elements form stable molecules when they have 8 total electrons surrounding them. If you have something called a single covalent bond, you have two atoms sharing one pair of electrons, so that would be represented by one line. Double bonds, 2 pairs of electrons, and then triple bonds, 3 pairs of electrons. So that's basically review. How to construct Lewis structures of molecules, we go over in Regents Chem, but I just kind of give you a list of things you should memorize. Here you really have to be comfortable with how to construct these Lewis structures because you'll be given some like off-the-wall molecules. So the steps you're going to take is you're going to add up all the valence electrons of the atoms that are involved in the molecule. So for example, carbon tetrachloride, 1 carbon has 4 valence electrons, 4 chlorines have 7 valence electrons apiece for 28. 4 plus 28 is 32 valence electrons. So your picture has to show 32 electrons. Whether they're bonded electrons or lone pairs, that's up to you to figure out, but there's got to be 32 electrons represented. The next thing you're going to do is draw a skeletal structure bonding the elements together. The central atom is going to be the one with the lowest electronegativity, except for hydrogen. Hydrogen can never be in the center because it can only form one bond. So in this case, we're going to put the carbon in the center and the 4 chlorines surrounding it. We're going to bond them together. You always start with single bonds. And when you put bonds in, you want to subtract those electrons from your total. So I started with 32 electrons, and by drawing 4 bonds in there, I've already taken 8 electrons into consideration, which means my picture still needs to have 24 more electrons showing. Those 24 extra electrons are going to go around the outer elements first, and that will usually take care of things. So in this case, I have 4 elements and I have 24 electrons to distribute, and all those elements are the same. They're all chlorines. So I'm going to put 6 electrons, non-bonding lone pairs, around each of the chlorines, and then that gets rid of the 24 electrons. If I had any electrons left over after I completed the outer elements, octets, I would add those to the inner central atom. And then when you go back and check, every element has 8 valence electrons showing. Carbon, 2, 4, 6, 8, and then each chlorine, 2, 4, 6, 8. If you run out of electrons before the central atom completed its octet, so for example, this HCN, 1, 4, and 5 has to be 10 electrons here. So 2, 4, 6, 8, 10. If you run out of electrons, and like for example, this carbon doesn't have a completed octet yet, it only has 4 electrons, the 2 and the 4 here, you're going to form multiple bonds until it does. So I cannot make multiple bonds here because hydrogen can only have 1 bond, but I can swing electrons over and make multiple bonds between the carbon and the nitrogen. When I do that, now that central carbon does have 8 valence electrons showing. The nitrogen has 2, 4, 6, 8 electrons showing. And I still have that single bond. So in total, I have 2, 4, 6, 8, 10. Some simple geometry terms that you should be familiar with at this point. If you have a linear geometry, it's a flat molecule. All of your diatomics, all of your Brinkelhofs would obviously be linear. Carbon dioxide is linear. A bent molecule will be at an angle with one single vertex. And that usually has to do with lone pairs involved. And we'll do simulations where you'll see this. You can have a pyramidal structure, which will be it'll be triangular, but it will also be raised. It will be a 3-dimensional shape because there's a such thing as trigonal planar, which would be a triangle in a single plane, looking kind of like a Mercedes symbol. But trigonal pyramid will actually be 3-dimensional. And ammonia has that because it has 1 lone pair and 3 bonding pairs. Then you also have the shape of tetrahedral, where you have 4 bonding pairs and no lone pairs. So those are terms just to kind of keep in mind for now, but we're going to do a lot more with molecular shapes. And there's going to be other shapes you need to know as well. Also a quick reminder about molecular polarity. If you see something about a polar molecule, which is different than a polar bond, remember polar bonds happen when you have an unequal sharing of valence electrons between unlike nonmetals. Polar molecules, amazing. Polar molecular geometry occurs when your molecule itself is asymmetrical in its geometry. And then nonpolar would be symmetrical. If you remember, the mnemonic device for that would be SNAP. Symmetrical molecules are nonpolar, asymmetrical molecules are polar. This will help you out with solubility issues. That water is polar, like dissolves like. So a polar substance would be more likely to dissolve in water than a nonpolar substance. These are just some examples of drawing some Lewis structures. So going through the motions here with like hydrogen, counting its valence electrons, each hydrogen has 1, so I need 2 total electrons showing. So I would write hydrogen next to hydrogen. I have no other choice. I would connect them with the bond. Oh, look, there's 2 electrons. I'm done. Water, you guys have drawn water so many times in Regents chemistry. Always draw it bent. So I have 2 valence electrons here, 6 valence electrons here. I have to show 8. So here's 2, 4 taken care of, and the hydrogens are done. I need 4 more electrons. 1, 2, 3, 4. Ammonia. Hydrogen has a lower electronegativity than nitrogen does, but hydrogen can't be in the center. So nitrogen is. It's the same reason why oxygen's in the center for the water molecule, because hydrogen can't be. I throw the hydrogens around there. I needed 5 plus 3 is 8 electrons. Well, right now my picture has 6. 2, 4, 6 with the bonds. 2, 4, 6. The other 2 electrons will go on the central atom. There's the 8. Oxygen. Well, each oxygen has 6 valence electrons, so I need to have 12 electrons in my picture. So I can start out by doing this. Okay, so there's 2, so I need 10 more. Well, if I do this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Well, that doesn't work because I've run out of electrons, but I don't have completed octet. Another option I could do is this, but that doesn't look right because now this one has enough, but this one doesn't have enough, so I'm not going to do that. So instead, what I'm going to do here is I'm going to swing these over and make a double bond out of them. So oxygen has a double bond. Don't worry about the placement of the lone pairs, just put them around the outside. But I do have 12 electrons here. I have 2, 4, 6, 8, 10, 12. And I've also completed the octet for each oxygen. 2, 4, 6, 8. 2, 4, 6, 8. Let's memorize that oxygen has a double bond. CF4, carbon will be in the center. It has 4 valence electrons. Each fluorine has 7. So you would surround the carbon with fluorines. Anytime you see carbon and 4 around it, you know it's going to be tetrahedral. So that took care of 8 electrons, so I have 24 left, and I will distribute those equally around the molecule. If you do not remember to put those electrons in, your structure is wrong. Nitrogen, this one, if you remember from Regents chemistry, this is the one that has the triple bond. So if you just memorize, you're kind of good there. Si2, well, sulfur has 6 valence electrons. Each iodine has 7, so that's 14. So my picture has to have 20 valence electrons. Sulfur has the lower electronegativity, and I'll put the iodines around it, connected with a bond. So that took care of 4 electrons, so I have 16 left. The iodine right now is showing 2 valence electrons, so let me do 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. So I just drew 12. So I have 4 electrons left. Oh, look, sulfur only shows 4 valence electrons right now. 2, 4. So 5, 6, 7, 8 will complete it. This actually, if you build this, would take on a bent shape like water does. But again, for now, just make sure you get the arrangements right, and then we'll talk about how to figure out geometries later. Fluorine is very straightforward. 14 electrons. Pi3, well, phosphorus has 5. Each iodine has 7, so 26. Phosphorus will be my center. Iodine, iodine, iodine. Well, that's 6 electrons gone, so I have 20 left. Let's complete the iodine's octets. Each of those gets 6. So that's 18. So I have 2 left. Where those 2 go? Right on top of the phosphorus to complete its octet. So this would have the same molecular shape as ammonia. And then SiH4, silicon has 4 valence electrons. Each hydrogen has 1, so 8. So I would do silicon, hydrogen, 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 hydrogen. Then connect it with the bonds, and ta-da, I'm done. Look how exciting. You might notice a pattern here that if you have like 4 total elements, it's a pyramid. If you have 5 total elements, it's a tetrahedron. But it's not always that simple, because we're going to go into more shapes. You're going to end up with things called T-shaped and seahorse. Oh my God, sawhorse shaped. The other thing to look at is if you do draw a molecule, you should be able to indicate its polarity based on its electronegativity values. So something like HCl, chlorine has the higher electronegativity value, so the polarity of the bond is towards the chlorine. So you would draw an arrow. Actually, sometimes you'll see it like this, with like a plus sign here, to form a partial positive charge on the hydrogen, partial negative on the chlorine. Okay, so these are just examples of simple molecules that follow the octet rule. I'm going to go over in the next video. It's shorter. It will talk about there's certain exceptions to the octet rule and how to come up with those.